We are going to see here another example of a boundary condition in order to implement it as a boundary condition, the matrix representation, again, of the full implicit method for the Black-Scholes equation. So the one we are going to consider is the following. So usually, for most contracts, very close to S equal 0 and for a maximum S, what we have is that the value of the option is linear. For example, it could be like value of representation of the value of the call option as a function of S at, when the contract is fixed, and could be something similar to that. So very close to the smallest values, and also for very high S values, you have that it's linear here. So basically means that both at s equals 0 and for very large values of s, the second derivative of v with respect to s will be 0, because if it's linear, it means that the second derivative it's 0. So it's an approximate boundary condition that we could also consider in this case for to be applied for as a boundary condition, as general boundary condition for the option. In this case, it's general because it's independent of the type of the contract we do have, because it's satisfied both for call options, for put options, or for different options. So that's why it might be quite useful. So in case that the payoff is almost linear in the underlying, we have that this satisfies. And so we're going to implement that on both sides at s equals 0 at the maximum s. So for that, we are going to consider a finite difference representation for the second order derivative of b with respect to s. And this is, we already know how to do that. And this is the finite difference representations we do have on both sides. This one is on the close to s equals 0, and this one is close to s equal s max, where in this case the maximum n we do have will be, index will be ns. So as you can see here, because it involves 3 points, this finite difference representation is centered around 1. And it's, of course, it's satisfied, this condition is satisfied at any time. That's why we do have the finite difference representation involves any j component here. And the same for the one corresponding to finite difference representation corresponding to the second order derivative of b with respect to s evaluated around s equal s maximum. In this case, this one is centered around index corresponding to the s variable of ns minus 1. So again, it involves the evaluation of 3 different values of the option. So it basically means, therefore, as the second order derivative of b with respect to s is equal to 0, that it means that this one, this numerator, is equal to 0 on one hand, and this numerator has to be also equal to 0 in this one. So from here, from the first one, we can extract an expression, we can clear from here an expression for v0j, and this is the one we do have. That's the condition. The value of the option evaluated at s equals 0 has to satisfy at any time, so at any j index. So as you can see, it's related with the value of the option at points 1 and 2. And the same we can do with the other side. We can extract from here an expression for the value of the option evaluated at the maximum index on the s variable, which is ns. And doing that, this is the expression we do have. That will be an s here. So here we have an expression for the value of the option evaluated at index ns, and again at any time. As you can see here, this one is related with the values of the option at the 2 different s values. So these are therefore the boundary conditions and the finite difference representation of the boundary conditions we do have on the 2 sides that we need to implement on our matrix representation. And this is what we are going to do next. So again, this is the matrix representation we just derived or the fully implicit method. You can see it depends on these capital A, B, and C parameters that we defined previously in order to make the matrix representation look nicer and shorter. So this is the one we do have. And then we need to include the boundary conditions that we have just write. So basically means that these two components here in this vector again, they are not independent from the others. So if we know the others, we can also use in that expressions, we can derive these ones. So we can consider them to be known functions of the others. So the basic ingredients that we need to know in order to have all the information on the option at any point in the S variable are these ones. And again, the center of the matrix is applying to these components here of the V vectors are these ones here. Okay, that's going to be our square matrix, because the aim here again will be to transform this matrix, which is not non-square matrix, into a square matrix. But what we need to implement here the boundary conditions. So besides this square matrix here, we have also need to include the effect of multiplying the contribution of this A evaluated at index S1 times this one. This is on one hand, and as this one is related through this relation with V1j and V2j, we need to include here a component here that will be the one coming associated to this one, and another component here, the one associated to this one, and that will be, therefore we need to include here another component, will be plus 2 times, because this is A times V0, but V0 is A times A evaluated A1 times B0 evaluated at J plus 1. But this is actually this one. So A1 evaluated at J plus 1 is going to be multiplied by B1J plus 1, because everything has to be evaluated here at J plus 1, minus B2 evaluated at J plus 1. So we have a component here which is associated to V1, which has 2 times A1 at J plus 1. So we need to include here a contribution which is plus 2 times A1 J plus 1. And another contribution here is coming to the one associated to the element V2, which is minus A1. So here we have to include another one, because this is the element that's going to be multiplying with the V2 contribution here. So we need to include here the element which is minus A1 evaluated at time J plus 1. And the same, we have to do the same with the one we have here in the bottom, with the last element here in this matrix. We have the product of this C element times this V component evaluated at index NS, but NS is equal to this relation here. We have this relation here. We can substitute NS with all of these. That will imply to include another component here. That will be that 2 times here, 2 times C, this C. I'm not going to NS minus 1 and J plus 1, and another one that will come from multiplying this one with the C element, which is minus C evaluated at NS minus 1 and J plus 1. So this is the element that we need to include also here. So just including these elements here in this square matrix, we're getting the same effect as the product of this non-square matrix with the whole elements here. So just implementing these relations between the B0 element with the 1 and 2 elements, and the B and S element with NS minus 1 and NS minus 2 elements coming from the boundary conditions. So doing that, that's the this is the matrix representation that we do have in this case for the full implicit method in the Black-Scholes equation. The one that already includes the kind of these general boundary conditions that we have just considered, corresponding to the second order partial derivative of the option with respect to the s at equal to 0 at the both sides at s equals 0 and s equal max. So in this matrix representation, it's already included these boundary conditions. So as you can see here, we just have this square matrix, and that we're going to call it, and we call it the M matrix, is on the left, evaluated at time j plus 1. These are the column elements with basic elements that we need to know in order to fully or to have the full information on the values of the options, because the ones we have at the borders are related with these ones. Evaluated at time j plus 1, and this is the v elements evaluated at time j. From here, again, our aim is to have clear from here the values of the option at time j plus 1 as a function of the values of the option at the previous time step. But this is quite straightforward to do, because now this matrix is it's a square, and now we can invert that, and doing that's very simple. So we have that the values of the options at time j plus 1 is the inverse of this square matrix times, which is a known matrix, times the this v vector evaluated at j. So in this case, there is no column, R column, that including the boundary the boundary information on the boundary conditions, as we already had in the Dirichlet boundary conditions. In this case, there is just a relationship. The V0 and the Vn, they are not having fixed values, but they are just having a relation between with the previous V components. And that the way of implementing that is just adding other components here, or the contributions here in this square matrix. That's why we don't have a contribution associated in this case to this new column vector that we are calling the R vector. So in this case, this R vector we're defining that was on the left at time j plus 1, it's equal to 0. There is no contribution here. So this is therefore the kind of matrix representation that we can implement now numerically in order to solve this equation, extract the information from the options at the next time step as a function of the previous one, once you have included this kind of boundary conditions, general boundary conditions that we can apply for most of the contracts.